Okay, let's start with the second session of today. I'm pleased to welcome back Leo de Moura and Sebastian Ullrich to talk about metaprogramming in Lean 4. Take it away.
Okay, thanks, Loris. So yeah, this is like more of a tutorial today, showing you the ropes of how to do basic metaprogramming, giving you some insights into how that works. I think, at least speaking personally, after we've already expended all our energy on the talk and released on Monday, so let's take this one a bit slower. And if you have any questions at any time, I think feel free to ask them during the talk. Okay, so I start today, and then Leo will take over the second half roughly. And let's start by a rough overview over how does the Lean 4 frontend look like, and where can you actually jump in with your own extensions. So yeah, there's a parser. There is, you might have heard about something called elaboration, which takes the parsed syntax tree and turns that into something the Lean kernel understands. And now we have an extra step in between in Lean 4, which is called macro expansion. So let's start at the top. At the top, the parser, very roughly, you can see as a function that takes a string and returns a syntax tree, which in Lean 4 is the syntax type. There are, of course, a few more inputs, and there are exceptions as output and so on. But yeah, at least today and in my talk, we won't care about types much at all. We won't see them. We'll simply work on a much higher level. So yeah, doesn't matter what a parser actually is. Yeah, when the parser has finished creating a syntax tree, it is then expanded. All macros inside of it are expanded iteratively. Meaning, a macro really is something that takes a syntax tree and creates another syntax tree. And yes, there is some monad involved in there, which we'll get to later. And so this is actually not exactly a pipeline like described here, but macro expansion is in fact interleaved with elaboration. So at least at each level of the syntax, we first expand all the macros at the top level, then we elaborate the thing, like give it meaning in the primitive way, and elaboration usually will then recurse on subterms, on subsyntax, let's say, which again will mean that this subterm will then be expanded maximally again, at which point elaboration will again apply a rule. So elaboration then is basically the last step that takes a syntax tree and creates something the kernel understands. So for terms, that is the expr basic data type that I think Leo will describe in more detail later. And there's another monad involved that can give you some more context, some state to work with. I should probably say, like in Lean 3, elaboration really was just used to mean term elaboration, but in Lean 4, where we more strictly make a difference between the parse, like where the parser really just parses stuff and does not actually process it on the top level. We also have, we talk about command elaboration, which is something that takes the syntax tree of a full command and, well, actually returns nothing, returns unit, because all command elaboration rules do is change the environment that is encoded in the state of the monad. So we only run command elaboration for the side effects that change the environment inside the monad. And then there are a few more levels like universes and tactics that have their own elaboration loops, basically. And at least for tactics, Leo will get to that later. And yeah, universes are pretty boring. They are also not exactly extensible because there's not much interesting to do there. So yeah, we'll skip over these, I think, in today. Okay, and then there's actually a reverse pipeline, basically, for the printy printer, which has a few steps. But yeah, we won't talk about that today. We really don't have enough time for doing that as well. Yeah, so I start now with the parser and the macro expansion, talk about that a bit, and then Leo will take over for the yeah, more involved stuff like elaboration and tactics. Okay, so let's start at a very basic level. So notations. You probably all know from Lean 3 that you can create infix notations, prefix, postfix, left associative, right associative, and it just looks pretty similar in Lean 4. So yeah, small syntactic differences. The only real difference you could perhaps see here is that the precedence, which yeah is basically the order of operations, which are these numbers, it's is now applied to the keyword itself, to the whole parser, instead of the token. And yeah, that is a actually fundamental change in Lean 4. And to give more sense to that, it's probably better to first expand all these very basic keywords, because yes, all of these keywords are in fact macros for the more general notation keyword. So if we do that, we see, yes, well, an infix notation like plus is actually a notation that first takes a left-hand side, then the token plus, then a right-hand side, and expands to the basic function applied to the left and right-hand side. And now we see that left associativity means that the right-hand side is parsed with a higher precedence than the notation the parser has itself. And yeah, I think now I can give a pretty intuitive understanding of precedences. This simply means that since the precedence is higher, the notation itself does not fit into the right-hand side, and we get the basic semantics we expect of left associativity, that it can only nest to the left and not to the right. And I think this was much more complex, or at least confusing, in Lean 3, where precedence was associated with tokens. And in fact, it also means that now we have the subtraction minus and the negation minus below, in fact, can have different precedences. So we don't have to decide which one of them is the true precedence. They are completely independent, which is also great for extension if you want to reuse any of these tokens in your own syntax. Okay, is there anything else here to explain? So one thing I should probably mention, if you want to play with this, how do you actually see what macros expand to? It's not pretty yet. Like we've been asked on Monday about, do we have a macro debugger or anything? So we don't. What we do right now is simply we set the trace elab command option, which will print out any command that goes through the elaborator, which does include commands from macros, and then you will get roughly the second output. And yeah, just one very nice feature, I think, in Lean 4. I'm not sure if you can actually see my pointer, but this in keyword you can now use after set option, sets an option only for the next command. And yes, this is simply a macro for a section that includes the set option and the command. So yeah, that's just one more nice application of macros. Okay, let's see. Okay, what else is there to say about notation? So yeah, notation, of course, can have more general shape than just infix, prefix, postfix. Like we can use tokens at any place. We can have more than just two inputs, like in the second example. And we usually talk of Mixfix notations in this generalization. But that's in fact it for Lean 4 notation. There are no other special forms like in Lean 3. There was this very complicated declaration for like iterated notation for list literals, for example. And yeah, you really in Lean 4 you should simply use a recursive or a recursive macro or yeah simply macro for that. And I think Leo had one example of that in his talk on Monday. Okay, and there's probably only one more thing I should really talk about for parsing, which is what happens if you create an overlapping notation. So for example, we could create this notation here, which also takes a plus, but yeah, actually takes another plus and another operand with the same precedence. And just to make it clear, this actually here translates to A plus B minus C. So if we evaluate a summation of at least 3 operands, like 1 plus 2 plus 3, we can see here that the new notation is taken and the result is in fact 0. So how does that happen? Why did it not take the ordinary plus? And so whenever the parser has the choice between using two notations, it applies a longest parse rule, meaning yeah, the one parser that does more progress on the string wins, even if it fails, because usually that's like the more relevant error message for users. And yeah, I call it a local rule here because you could say, well, if you look at the entire string, we can of course parse that string with either parser, but at the point of the first plus, when we try to find a parser there, we find that the regular plus parser only parses up to 2 because it is left associative. And yeah, our new double plus parser will parse the whole thing, so it wins. And that is what I mean by local longest parse rule. Okay, that should be pretty much it for for notations. We can go down one more level by expanding the notation keyword, and then we get a syntax declaration and a macro declaration. And we get to macro declarations in the next part, but syntax here means, yeah, you see it looks pretty much like notation. It just tells you more explicitly what is the nested parser we're using here. So the E above is actually parsed as a term, like not a command, not a universe, but a term. And this syntax, this whole syntax again lives in the term syntax category. So we have multiple syntax categories in Lean 4. Term is one of them. We just call it term because we already have the expert type like on the kernel level. So we use term for the syntactic level. But yeah, you've basically seen all the other categories on the first slide, which is command, level for universe, and tactic. And in Leo's talk, you have also seen the STX syntax category, which we use for creating the syntax of the syntax keyword. There's some nesting going on there, but I don't think we'll get to that category today. Okay. And you can, of course, declare your own syntax categories. So there's a declare syntax cat keyword, and you give it an identifier. And after that, you can create new syntax in that category. And you can then, in the last line, use that new category inside other parsers, and then it will try to use any of the parsers you have declared in that category. Okay. There's a bit more going on about syntax. I can't go through all of that given the time, So you can have syntax abbreviations, meaning, we can write syntax. Binder ident should be, should stand for after the colon equals for an identifier or an underscore. And yeah, in the next line, there's another abbreviation that uses like a plus for iterated parsing, often by the binder ident, and a question mark for an optional syntactic part. And yeah, another example you've seen in Leo's talk is like an even more interesting or complex postfix operator, like the comma, star, comma, question mark means parse the thing before it many times, separated by commas, allowing an optional trading comma. Sorry, was there a question?
Can I ask, can I make a remark about this last trailing comma? I mean, the reason why people like to put that last trailing comma is simply because Lin3 won't show you the goal accomplished tactic state if you don't put it.
Buzz.
Right.
Not because we find the comma is beautiful. It's because we want to get our reward, the goals accomplished message.
Right. I don't actually remember.
So shows the goal accomplished, and we don't care about the trailing comma.
Right. If you leave out the trailing comma, does it show it on the end? If you already have an end? I really don't remember.
No, it shows nothing.
Yeah, you can't see it. That's why you have to put the comma if you want the goals accomplished.
Right.
Okay.
Yeah. I think, just experiment with that in Lean4 if you like the comma-less, like completely comma-less syntax we have. And otherwise, I think, there should be a way to do this without commas and still making everyone happy, right? Like there should be a good way to display goals there. Okay, but I think we have a few other places where we actually use that. I'm not completely happy with this syntax, but if someone else can come up with something that says, something separated by commas, but also with a trailing comma, then come to me, I guess, and talk to me. Okay. Okay, let's finish with parsing, because parsing is actually not that.
Does this have like the problem with, like, if I have like another end inside the begin and end, we match the wrong end? You know what I mean? Like if let's say I have another begin end inside the begin end, we would match the wrong end. Like we would do the kind of like the greedy match of end, and when they see end, it freak out and this is like the end that I was.
That shouldn't happen, because I mean that is basically bracketing, right? Like you have a token at the very beginning and at the very end. So the nested parser of the begin end will only finish when it has seen its end, and then only then will you basically come back to the outer parser expecting another end.
I see. Yep, makes sense.
Yeah, so if you have a token in front and token in the end, that's already usually perfect. Then you don't have to worry at all about like syntax flowing into other syntax. And of course, we don't do that anymore in Lean4. Like we have by instead of begin end, but we use indentation instead to solve this very issue. Okay, one more thing about parsing. So if you ever look at the syntax of like building commands and so on in Lean, you will see that it looks a bit different, which is simply that like it's using basic defs of a parser type. And the simple reason for that is that we used the upper syntax to implement the lower syntax eventually. So we would like to unify those two, at least syntactically at some point, but right now we have like these somewhat different styles. But if you ever see something like a def with this parser bang macro and then multiple terms separated by this double crater, then simply think of it in the as the lower example, like, so a basic def is just a syntax abbreviation, and then the right-hand side is, yeah, just remove the greater thans. And yeah, if you see like an attribute like built-in term parser, that simply means it's a syntax. Wait, why is it? Oh, yeah, sorry, that the category here should be term, not command. Yeah, if you see such an attribute, it simply means it's creating a syntax in that specific syntax category. Okay. So yes, in summary, parsing is based on syntax categories, which are each.
Sebastian, I didn't understand the previous slide. So in the end, do we still need to learn about those parser combinators that we have in Lean3, or will we be able to use the new way of doing things even when defining arguments of tactics and stuff like that?
Yeah, if you I think I have some echo. Not sure where that's coming from. Okay, it's gone. Great. If you only write tactics, you should not have to think about the upper syntax there. Only when you like go into the Lean source code to find out how a command is parsed, like structure or something, you may have to see this. Yeah, I think that's the right answer, Leo, right? Okay. I'm not hearing any. Okay, so let's just go forward because I think I'm already a little slower than I expected. But yeah, so parsing is based on syntax categories in Lean4, which each are basically a precedence parser composed of parsers. And yeah, there are leading parsers and trailing parsers, which simply means do they start with a token or do they start with this category? And yeah, if you know anything about parsing, you might know that this is important to avoid left recursion, but otherwise you can completely ignore this distinction because syntax will do it for you. And yeah, the one, at least, well, one big change in Lean4 is that precedences are now per parser and not per token. And we follow the longest parse rule whenever we have like the choice between multiple syntaxes in a syntax category. If we use the or else operator instead, like I had, I think, on one slide, then this is actually not true. Then we really just try the first one, and only if it fails without consuming any input do we try the second one. So basically the or else operator is left biased, but basic syntax declarations in a syntax category are not. Okay, so much for the details. If you want to know even more details about how the parser actually works on the low level, I wrote a pretty thorough, I think, docstring in the parser file, but yeah, as I said, otherwise you should not have to think about this detail. All right, so let's continue to macros now that we know that this syntax notation actually does. So we had this very basic macro before with parentheses, and probably this macro rule can intuitively already be read. It says like, whenever you see the syntax of a parenthesized term E, turn that simply into the term E itself. And so we have this backtick parentheses to say, okay, here comes a quoted syntax. And then we have the dollar anti-quotation that does the opposite thing, that says, okay, this one is not part of the pattern. This is actually like a variable of the pattern and of the quoted syntax, like a placeholder. Yeah, and this can actually be written in just slightly another form, just if you ever see the macro keyword. So just like notation combines syntax and a macro rule, macro does the same, just with the more general syntax syntax. So you see the syntax category is now explicit, and the right-hand side also is not just the term to translate to, but an actual Lean program creating the syntax. It should be translated to. And yeah, if you wonder, do we even need a quotation here on the right-hand side? The answer is no. If you just want to return E, like in this example, you can also just do that, because the right-hand side really is an arbitrary term of type macro M syntax. And yeah, that is actually what is going on. If we go one level lower, so this is the only time I think I'll show actual types, actual def, well, except for the example before. So yeah, when you write a macro rule, what actually happens is you have a regular def of type macro, which is an abbreviation of syntax to macro M syntax, and we apply the macro keyword to that with the name of the parser it applies to, which in this case is auto-generated from the syntax command. And then we immediately match on the single syntax argument. And you see we just copy basically the macro rule in there and then give it one last default case, which throws an unsupported syntax exception. So if none of the macro rules match, you will see this exception. And we actually call this definition simply my macro, which is completely fine in Lean 4 because you can see these crosses, which Leo has already explained in his talk, which so just to recap, these are the result of macro hygiene, meaning any identifiers that have these crosses cannot be accessed in the current environment. So you cannot write like #print my macro after using this, after declaring the macro above, because the my macro keyword will not actually be accessible by you. And also vice versa, these identifiers cannot access the environment they've been expanded to. So even if you have defined your own throw declaration, it will not break this macro because it will always refer to the throw declaration when this macro was defined. That is creating this my macro definition. Okay. And there's one more thing this unsupported syntax is doing here, not just doing a nice exception, but it will actually cause the macro expansion to try other macros that may succeed instead. So macros are extensible in this sense. So we have in the supplement of our macro paper and also in our test suite, if you want the a refreshed example, we have this example where we have like an extensible notation for arbitrary big operators. And without going into the details here, so we can say we have a new syntax how to like basically sum or do a product over things and then give a new macro rule for something we have already given a macro rule before, using this new notation, and then we can immediately use this new notation with the intended semantics. All right. And the basic semantics of that is just like elsewhere in Lean with instances and so on. We always try the newest macro first, so basically the bottommost, except if you give it a specific priority. Okay, so now let's get to one more fun thing, which is these quotations in detail. So here I have a very nice specimen from somewhere in our code, which basically matches the most general syntax of a let, at least if it like loses the colon equals and not equations and so on. So what is going on here? So first of all, any quotation has the type syntax, at least in patterns. So you can use it, as we've seen, to match against other syntax. if you use it in terms, it actually has the type M syntax, where M is any monad, given that this monad implements some monad quotation class, which all is used for implementing Hygiene. Okay, and then we have like basic anti-quotations in there. So if you look at the last two, val and body, these simply have type syntax because they match a subterm or a sub-syntax, I should probably say. And something more interesting is going on in between. So there is this dollar binders, which itself is surrounded by this dollar bracket with a postfix star. And that simply means, yeah, match the thing inside the brackets as many times as possible, and yeah, accordingly bind the anti-quotations inside to all occurrences. So yeah, this binders anti-quotation actually has type array syntax for all occurrences it matched against. And similarly, if we use the brackets, dollar brackets with a question mark, we can match an optional syntax part. Like here, there's an optional type. So we say, yeah, optionally, a let can also have a colon followed by an anti-quotation. And if that matches, then the anti-quotation will have the value option.sum of the matched syntax. And if that colon and term did not exist, then it will have option.none. And yeah, in this case, so the question mark here is actually part of the anti-quotation name. It's not special syntax, while the outer question mark means, yeah, this part is optional. So we have some slightly unfortunate clash between our naming convention using question mark for things of type option here and our syntax. Yeah, not sure if we can improve that in the future. Yeah, and just to give one more example, you might see, which is not in here, if you have an anti-quotation followed by comma star, this actually has a different type separate, which gives you access to both the elements and the separators, should you, for some reason, like, I don't know, formatting or so, need the separators as well. Okay, and finally, I should mention what this colon ident here means after it, right? Like that's not clear yet. And this simply means parse, like only match the output of the ident parser at this point. So you can use that when anti-quotations overlap. And so where do they come from? Whenever you use a syntax abbreviation, like syntax foo : equals, that introduces a new anti-quotation kind, foo, you can use after an anti-quotation to say, yeah, I only want to match parts of this syntax. And yeah, so if you like have nested syntax, you can basically specify the level of nesting you want to match here. And if you declare a new syntax, you also get a anti-quotation kind of that name, and you can also get a quotation kind on top. So if you inside a quotation first give a name of a category and then a pipe, it will parse the remaining quotation using that category. So you could, for example, use that to quote a universe term, for example, because by default, quotations will only parse terms or commands. All right. So let's see, what else is there to say about macros? So I've given an intuitive understanding of Hygiene, but might not be clear quite yet how it works in practice in implementations. So let's say we have the simple macro that simply unfolds to, well, we first use a quotation of the identifier raffle, and then we insert that into a function with an argument raffle. And so, yeah, it's not intuitively completely clear what should happen here, right? Like, is this the identity function of raffle to raffle, or is it should this be the constant function of anything to the global declaration REFL. Like, do these quotations see each other, see their names, or do they not? And yeah, we simply took the practical route here, saying you probably want to write your macro using multiple quotations, or be able to do that, which means, yeah, this is in fact the identity function, because Hygiene in Lean works per macro, or is scoped per macro. And yeah, I think this is exactly the same as in Scheme or Racket, as far as I know. And yeah, just as a final example, you can also create nested hygiene scopes with. Oh, I copied completely the wrong name. What I wanted to say is you can create them using fresh macro scope. So yeah, just as a final, more complex example of a macro, or even a part of a macro, this is the part that when you give equations after a def, unfolds that into a function following a match. So yeah, in the very end, we say like we want to create a function. Sorry. I should have said, like, when we have 0 arguments, we create a match matching on the. Okay, yeah, I took a wrong turn here. So let's say that I want to create n new names in a macro, like a dynamic number of names. So I can use fresh macro to create like a new X here. And whenever I call fresh macro again, like recursively, this will create a distinct X. And so I can use that to create like basically X1 to Xn without actually having to come up with names and having to care about that. Okay, I think with that, I will summarize macros and then pass over to Leo. Yeah, so macros are syntax to syntax translations. They are applied iteratively, like exhaustively, and also recursively on subterms, at least when the elaborator calls back into the macros. And they are associated to a specific parser, and all macros of a parser are tried in a specific order, like newest, except when given a specific priority. And all of this is well behaved by Hygiene, meaning the name capture and semantics should be what you intuitively expect of them. Okay, I think this was pretty fast, but I still took some time. So yeah, I think if there are questions about syntax macros, this would be a good time. Otherwise, Leo should go ahead.
Well, let me ask the same question that I asked you last time again, which is about the missing thing. So, I mean, I still do not understand. Is that like something that come out from the parser, or is that something that you kind of like infer after you perform the expansion and know that, oh yeah, this is something that is going wrong and is missing something?
So if I understood your question correctly, it's about, like, is it about how to elaborate, how to expand like partially incorrect syntax?
Yes. Yes.
Okay.
Yes.
Yeah. So that's a great question, and we are still working on that. Let's say, like, we definitely want to do this, but like right now, we're not doing any elaboration at all if there has been a parser error, and so the basic syntax type has an actual constructor called missing for doing that. And in fact, if you match on a partial syntax tree and something is simply not available, that if you use an anti-quotation, that will be assigned the missing value. So we have the infrastructure in place, but we haven't actually used it. It's not in use yet, really, in the elaborator.
Right. But my question is that where does that come from? How do you figure out from the parser that thing is missing? Because like, for example, you know that if must have 3 branches, must have 3 parts, right? It must have the conditionals, it must have the then branch, and it must have the else branch. But if you have the input from the macro that expand to if, and it just has only 2 branches provides, how do you figure out that, oh yeah, it's not going to expand to 3 branches later and something is missing? Does that make sense?
See if I understood you correctly. So, I mean, so this anything you write in quotations still has to parse. Like if you don't write a valid syntax if statement inside your quotation, your macro won't even compile. I'm not sure if that already answered your question.
Yeah, we can take this offline, I think.
Okay, yeah, that's probably better.
Thank you. Yep, thanks.
When you say that a macro is associated with a specific parser, you mean like the parser for parenthesized expressions, like that's what you mean by a specific parser?
Exactly, right? Yes. Yeah, I didn't talk about that too much. Like you saw the single macro attribute applied to like a parser name. That's basically happening what's on the low level. And yeah, we simply check like what syntax are you using, what parser are you using in your quotation of a macro rule, and that's the parser rule associated to like for you basically. Okay.
Can I ask a question about slide 3?
Yes. Okay.
On the bottom half, you said that the precedence is attached to a parser, and I see 2 numbers there. What are the 2 parsers in that first example, the second half?
And the first example is the plus, right? So after the notation, that is the precedence of the current parser being declared, like of the plus. And the second one, the 66, that is let's see, it's the maximum precedence that is accepted for any subterm in this position, like for other parsers that follow the plus.
I see. Okay.
And yeah, I hope that was the right way around. Like I'm never sure if it's lower or maximum or minimum, but yeah, I think it should be correct. Okay, Leo, do you want to take it from here?
Yeah, sure.
Yeah, I hope I still have given you some bit of time left. Okay. How do I escape from here?
Can you see?
Looks good.
Looks good.
Yep, I can see.
Yeah, I'm going to start saying that I'm new to this technology. I realized that I spent half of Sebastian's talk answering. I thought I was answering to everybody, but I was sending messages, private messages to Richard. Then I also reply to everybody when people ask us in private. Sorry about that. I'll try just to give an overview of how to declare elaborators and tactics.
Now you're not yet in full screen.
I'm not.
No.
Maybe I have to stop.
Yeah.
That's what's happened. Yes, I have to put in full screen.
And then share.
The reader, yeah, and then share, right? Okay, I'm in full screen. Let me go back. Now it's in full screen, right?
Right.
Cool. The link package, right? Oh, I'm hearing the echo is gone, I think, right? Okay, the link package. The link source code is in the link package, right? And in the link namespace. You don't need to import the link package to use link, right? Many extensions can be, all the extensions that Sebastian described as the macros, all this stuff can be done without importing the link package, right? So you don't need to get a dependency on the link package to create this kind of extension. But you need to import the link package in the following scenarios. You want to manipulate the kernel expressions, the kernel environments. You want to write decision procedures. You want to write your own elaboration functions, right? These are scenarios where you need to import lin, right? And if you want performance, you can create a plugin. In the future, I hope we are going to be able to also just-in-time compile your code, and maybe not even this extra step that may be annoying to a lot of people can be avoided. I think macros are very powerful. Most of things, actually it was hard to find examples to demo here. I mean, most things we do using macros. And there are some, then they decided some useful information, right? Even if you don't care about writing decision procedures, there are some terms that we call helper terms, that are terms that help you to create macros, right? First, one example of is this special let, that it changes the elaboration order. By default, a let will elaborate the value, then we elaborate the term, right? This let star allows you to elaborate T first and then elaborate the V, right? This is very useful when you're implementing things that have join points. Join points is roughly a go-to in a pure language. We implemented do.gsl using this let star. This way, it may be handy. I'm telling you this may be handy when you're creating your own macros and you want to force lin to elaborate things in a specific order, right? The type of is another helper that allows you, it elaborates T, infers the type of T, and puts the type of T there, right? For instance, here's a tiny example where I'm saying, just define this example that takes a net and returns the type of X instead of being net. This is equivalent to writing net here, but this is super handy when you're creating complex macros. Another useful helper term is this ensure type of, that you have two terms, T and S, and a custom error message, right? For instance, here's an example where I have the Y, I have ensure type of, I'm trying to redefine Y, and I'm saying ensure type of, this term here must have the type of Y, that's a net, but here is a Boolean, right? And you get this nice error message now, right? Invalid reassignments, term has type bool, but is expected to have type net, right? This is also helpful when you're creating your own GSLs, right? I mean, this is actually an actual example. We have the do GSL. This is what when we have that mute that I showed on Monday, the let mute, that allows you to reassign variables in for loops. It uses this helper term here. You're going to get an invalid reassignment error message instead of a type error, right? A generic type error. The expert now, if I want to write decision procedures for lin, probably you have to understand how expert works. It's a bit different. It's very similar to the lin tree one, but there are some differences. The differences are, there were a lot of confusion. In lin 1, we tried different approaches for manipulating terms. We try manipulating deploying variables directly. We tried the contextless approach for manipulating terms, that you don't have a local context. Your free variables, it's what you know by local constants in lin tree. They could have a pointer to, they would have information about its type and everything. You didn't have to have a local context. But eventually we settled by the locally nameless approach, but the leftover was there in lin tree. And many users were confused. Why do you have a type here in the local context? Why is this called a local context, a local constant? There are all this confusion, right? And so we clean up. We have bound variables, the bound variables, like in lin tree. A local constant now is named what it's the right name in the locally nameless approach is a free variable, right? In lin tree, sometimes we use free variable for deploying variable, the first one, but in lin 4 we use, if you're using the locally nameless approach, a deploying variable, if you try to hide bound variables as much as possible. When they pop up, we say that's a loose bound variable. It's something, unless you're trying to do something super efficient, you should never see bound variables, right? Lean is going to hide them. You have meta variables. The other constructors you are familiar with in Lean tree. Then we have the literal for string and natural numbers. We have metadata, right? That you can allow you to tag information. In Lean tree, we used to have a bunch of different identifiers for doing that. This is not ideal. In Lean 4, we have something called metadata that you can tag. You can store information on this field here called mdata. And we have projections. This is a kernel. They're efficient to process. Avoids a quadratic blow up when you're having many nested projections in Lean tree. If you're writing external type checker, that's one thing that's important. Or you're trying to export something. You don't care, things that you don't care. You don't care about meta variables. They are never going to be in the kernel. You can get rid of all metadata before exporting, right? Probably you don't care about the information. You can expand the literals, and you can get rid also of the projections, right? So if you're exporting a Lean development to external type checker, you may still have something relatively small. We use many different monads, right? This one is the one you are most familiar with, is the static monad in Lean tree, right? But we have many different ones. And the static monad in Lean tree originally was to create interactive statics, but people use it to create decision procedures, a bunch of different stuff. It was like, oh, when you have a hammer, everything looks like a nail, right? In Lean tree, it provides only the static monads, and so you use it for everything. But in Lean 4, we have way different monads for different purposes. The macro M, Sebastian described it, that's for macros. On the top of our hierarchy, you have this configurable I/O. It's like I/O, but the error, you can configure the exception. I/O is a special case of EIO. Then we have our core M, that's for basic infrastructure. Meta M is for metaprogramming in general. Term labs for writing elaborators for terms, something that converts syntax into a kernel expression. We have commands. Elab M is for elaborating commands. Simp M is the simplifier monads that you add a little bit of extra state to a meta M monad. And static M is the one that you are used to. That's where you have a list of goals that still need to be solved, right? I'm not going to go into extreme detail. I don't want to run out of time, but I want to give you some idioms we use, right? For instance, in Lean, we have these basic building blocks for writing our monads, like state ref t. That's is very similar to the state t you have in Lean tree. The only difference is that this state ref t can only be used on top of something that's on top of I/O or the basic ST monads. It's more efficient to generate code for this kind of transformer. But basically, you can read this core M monad the following way. You can perform I/O. We have this exception here. We experiment with different designs, but we settled with this one that we have in Lean tree, more or less a uniform exception type for our implementation, that you can have the error with some syntax object giving the context of the error. You have a message that contains a structure. You have structured data in this message. It's not like a monolithic, it's not a string, it's a structured object. And you have a constructor for internal error messages, something that you have to capture. You don't want to show to the user. It's an exception, it's an internal exception. The error is something that is user visible and internal it's not. And basically, let's continue to the core M. You have the EIO. You can perform basic IO with this exception here. We have this state and this context here. You should roughly view as the ambience. I mean, you have some information like read-only information in these monads. So you're going to see this. We use this idiom everywhere. Our monads are always adding more states and more ambient to the monad. Another idiom we use that you have to get used to if you want to write extensions to Lean. It's like you have these interfaces. I mean, for instance, the core M implements many interfaces. The interfaces always have the prefix monad, like you have here monad.ref, right? That provides two methods, getRef and withRef, right? So you have monad.env that you can get the environments and modify the environments, and so on, right? It's just to give you an idea that our monads implement different interfaces. The meta-m is the one that, if we're writing decision procedures, we are going to use it to connect, you're going to use it to manipulate the kernel terms. The general boilerplate for a decision procedure is you're going to design your own data structures for implementing, for instance, linear arithmetic. You're going to have a representation for linear inequalities. You're going to have your own data structures. But now you implement this, probably you have your own representation for proofs. But now you want, the first thing, you need two things to connect to a tactic. You want to be able to convert a Lean expert into your internal data structures. And then when you construct a proof using your data structures, you want to convert it back into an expert, right? That the kernel can process. And you're probably going to use meta-m to implement this bridge between your own data structures and the Lean expert data structures. You have, in the meta-m, you have the meta variable context. Meta variable basically is a whole, you can imagine as a whole that has a type and has a local context, right? And so this data structure contains all holes in your context. You have the cache, you have a local context, local instances for type classes, and so on. And the main methods that this monad provides is weak head normal form. You can infer the type of an expression. You can check if two expressions are definitionally equal or not. You can try to synthesize a type class instance. Here we have two versions of, we have a few versions of this method. This one here is the most general one that you provide the type. For instance, you would provide an example, inhabited bool. You want to synthesize a term of this type using type class resolution, right? You can have a bounds on the size of the term. We believe this is a much better threshold than the depth like we have in Lean tree. He's saying the size here is how many instances are you allowed to combine to create a solution for your problem, right? It's like, wow, if my solution has 100, I combine 100 things, this is probably not what I want, right? It's much better than the depth, right? And here there is a L option that can be some succeeded, none failed, and undef, saying, I may not do it right now, I may be doing later. This may happen when you have meta variables in your type. Type class resolution, you never try to assign a type that was created by typing rules, right? It doesn't want to affect the typing constraints. So, but you can try type class resolution there. Basically, if this meta variable, what this part that's missing is irrelevant, it will succeed. But this method here is going to say, I can't continue. There's information missing. That is the undef here. And you have also this make app m. Basically, you give a constant and an array containing the explicit arguments. This is also very handy because creating terms manually in dependency type theory using the APIs is very time consuming, right? Because you have implicit arguments, you have universes. This stuff here tries to use typing rules, type classes to optimize the process, make it more comfortable for you that are implementing automation. Here you have a very example. You can try. You open a browser, You open Emacs or Visual Studio Codes, and you can write this. You can say import Lean. Here I declare a function that's just for doing some tests. I'm opening the namespaces Lean meta, and then I'm writing a test here, a methods in meta-m units. Then the first thing I'm trying is to create an application of F that has the literal to as an argument. Notice that I'm only providing the explicit arguments here. I'm not providing the alpha, I'm not providing the instance. There is a universe hidden here that I also not providing, right? And you see that I'm using this trace message to print here. When I execute the example, I'm getting here T colon F2, right? If you want, you can say set option PP all, like in Lean 3, you're going to get the at f net, the net has add, something like that, and the 2 there, right? Then you can say, oh, put T in weak abnormal form and print again, and you can see the results. Then, oh, ask what's the type of T you get there, list net. Then, oh, let me create a meta variable with in the universe 1, right? Then you can say, oh, I'm going to create a term list of this, with this meta variable. I print, I get list of M5. The 5 here is the unique ID for this meta variable. Then we can say, oh, let's try to force this type and P to be definitionally equal. Lean is going to solve this unification, this constraint, by assigning M5 to net. If I ask Lean to print M again, I'm getting net here. I think most of you should be familiar with this kind of monadic code. It's very similar to what you have in Lean 3, but there are better facilities for manipulating, for tracing. There you don't need to have a fake tactic with fake goals for manipulating your terms. Yeah, and you can run your own file in your file.
Question, could you use the abbreviation where you put the left pointing arrow without the let inside the interpolated strings? Because
yes, you can. Yes, you can. You can.
You could get rid of all those let lines.
Yes, you can. Exactly. You can do that. And that's one beautiful thing about hygiene. Even if you do stuff like that, it works, right? These things are creating temporary variable names. There's no accidental name capture. For instance, in Lean 3, we had some string interpolation, but it was a big hack. It was a string. You're manipulating strings there. Here, we're manipulating syntax objects. The string interpolation is a macro. You can nest macros inside, and you are completely protected from accidental name capture. Here, I'm going to show an example. I think it's going to be my last. I have more examples, but I can show offline for you. I'm not sure if everybody's interested on this kind of stuff, but I can go over more examples offline. But I will try to finish with this one because it covers many details and many idioms that you are used to in Mathlib when you are writing your own tactics. For instance, reduce here, I'm writing something that's it's not going to put in weak animal form. I'm going to reduce the whole term, right? And I have a bunch of options here. I don't want to reduce stuff that's implicit. The user is not going to see anyway. Why I want to do that, right? I can also have flags to skip proofs. Since you have definition, you have proofing relevancy. What's the point of reducing proofs? I can skip types because maybe I don't care. It's just an example. The first thing, we start with a let's rec. That's this visit method, right? The first thing, it takes an expr. And the first thing, we are putting a monad cache transformer on top of it. Basically here is like terms in Lean are often DAGs, they're not trees. Right? And one common problem is to traverse a DAG as a tree. You can get exponential blow up. So you can avoid that using a cache to prevent you from visiting the same term over and over again. You just put this transformer on top of meta m, you get the cache for free. And you have this method, get cache, check cache. Basically what happens here is check cache E. If E is in the cache, you return immediately. Otherwise, you execute these codes here and puts the result in the cache, right? It does that for free. This example shows also, you may find this line a little bit weird. Why you are writing like that? Why didn't we write this way? This is because this is an anti-idiom. This is one of the traps of these nested methods. Suppose that you have written like that. What would happen? We would lift this application here and we would execute is type, even if its skip types is false, right? It's still going to, is type is not effectful in any meaningful way. Your code would still work, but you are performing computation that's not needed, right? This this variance of the these are monadic ends, is a way to view it, right? Basically, it's going to execute this action. If it returns false, done. It doesn't execute the other action. This is when with this monadic stuff, you can hide a lot of the complexity, but sometimes you have to be aware of these little things, right? And so this is one thing that you should be aware of. Let's forget about this detail for now. Let's focus on the actual example. Then I'm saying, oh, if skip types is true, and this is a type, I return. If it's skip proof is true and E is a proof, return. All these things are short-circuited. They are not implemented in the naive way. They put a lot of optimizations there to return true or false quickly when possible. Then we say, oh, put E in weak animal 4. Then we try, oh, if it's an application, get the function, get the arguments. This function info is an efficient way to find out what's the explicit argument, what is implicit, what is, if you have forced dependencies or not. Here we are just using this information to be able to check if something is an explicit argument or not efficiently. And we start traversing. If we have information available, we use it. If explicit only is not true, or is an explicit argument, we visit the arguments, right? We update args by visiting these arguments and update this array of arguments, right? Same thing. Then we return the updated application, right? So you have F here, that's the updated, where is, oh no, F is already in weak animal 4. We have the arguments, we update the arguments and construct a new application here. These two constructs here are super helpful for you. It's like it's a way to open a telescope. You have a bunch of nested lambdas. You're going to open this sequence of lambdas, right? All binaries are here in XS. This is the body of the lambda, right? And you can now traverse it. Why this is useful? Because it does a lot of magic behind the scenes, right? First thing, the lambda has de Broglie variables inside. It will create free variables, replace these de Broglie variables with the free variables. It's going to check if some of these new binders are local instances. If they are, it's going to validate your cache for type classes. It does a lot of bookkeeping for you, right? And same thing for all, right? Yes, basically this is, I had to order, but I can go offline on the other examples. But I'm happy to talk offline about metaprogramming, how to do it, go over some small decision procedure you may want to implement. But I think now is a good time to end. Thank you.
Yeah, thank you very much, Sebastian and Leo. Let's give them an applause. Are there any questions? We'll have a couple minutes of questions. We are indeed over time, but we'll eat up a little bit of the next break.
I know this wasn't really the point of the example, but you mentioned that whatever the Lambda helper function will invalidate the instance cache if it crosses a.
Yes.
So that means this by exacti stuff is no longer going to be a thing, right?
Excuse me, what?
We have, currently in Lean 3 we have to write things like for all G : type, square brackets group G, comma, by exacti, blah, blah, blah. So that issue
is gone.
Is gone. Okay, great.
No, it's a good thing, right?
Yes,
I hope so. There's a lot of engineering to make this stuff do what I thought you wanted.
That's very great.
That is definitely what we wanted.
Yeah. Amazing.
Yes.
Are there other questions?
Yeah, I'm gonna ask the second question. Is this visit? What's the type of B? Is it a list of all the binders or?
What type? Which one? The XS here?
Yeah, there.
Yes, this XS is an array of expressions. Are the three variables that were created to replace the de Broglie variables of the lambda.
Oh, okay. B is the body and X.
The body, yes, exactly. And here is basically here I open the lambda, did something with the body, and use this make lambda fvars to put it back as a lambda, right?
Mm-hmm.
And we use this stuff everywhere. I mean, if you see our code base, this lambda telescope is used everywhere. The same, actually, the for all telescope is used way more often than the lambda telescope.
Will you put these slides online somewhere so we can read the stuff that got skipped over?
Yeah, sure.
Okay, if there are other questions, let's ask them in the break.